now that we have defined the sheavification, we can return to this general project of taking all the definitions of commutative algebra dealing with modules and constructions with them and generalizing these to the OX modules on some scheme X. And so if you start, for example, with a morphism F between such OX modules, then you already find the kernel sheaf, and now the image sheaf is just the sheavification of the image pre-sheaf that we had. And one useful observation here is that we can apply the universal property to get a nice morphism of sheaves here. So if you look at F mapping to G like this, then first of all, you get such a triangle of morphism of pre-sheaves, which on an open set U just takes this map from F of U to the image of FU, mapping then into GU. So this defines this triangle here. These are all pre-sheaves mapping to each other. And then in particular, this gives you this, this map from this pre-sheaf to the sheaf G. And then by the universal property of sheavification, this map factors uniquely through this image sheaf, which is the sheavification here. So there exists a map F tilde from the image sheaf to the target sheaf G. And this is just kind of the fancy version of saying, well, of course, we expect that the image of a map should map to the target. So here we could use this universal property. And then with this being said, we can define what it means for this map here to be injective or surjective. It's injective if its kernel vanishes. So in other words, the kernel is the zero sheaf. The zero sheaf is just a sheaf which returns on each open set the zero module. And so that's how we expect. And for surjectivity, to formulate this, now we can use this image sheaf because classically we would say, well, the image should be everything. And in this case, we make this precise by saying, well, this map from the image sheaf to G should be an isomorphism. Note here that it's important to formulate it like this. You could also be tempted to say, well, F is surjective if on any open set the map from F of U to G of U is surjective. But in fact, that is not equivalent to this situation here. So it's really important to use this sheavification in this process if you want to get something nice out of it. So this was kernels and images. Then you also, a second construction which you can do is you can take quotient modules, right? So if you have an injective map here, then this does mean that on any open set U, this F of U is a subset of G of U as a module. So it's a sub O of U module. And then when you have such a submodule, you can always take the quotient module. And all of these fit together nicely into a pre-sheaf. So you call this G modulo prime F. Again, you will find that this is not a sheaf in general, doesn't satisfy this kind of unique Lewin property. But we can convert it into a sheaf by just taking the sheavification. And we call this the quotient sheaf. As you see here, we apply the sheavification as a kind of magic sauce. Everywhere where we get a pre-sheaf, we now just sheafify. So this was this, then some bit of homological algebra. If you have a sequence of morphisms of OX modules, then you call this sequence complex if the composition of two subsequent morphisms here is always the zero morphism. This is just generalizing the notion of a complex of modules. Then some kind of mini exercise here is that if you have this complex property, then this induces a map from the image of Fi to the kernel of Fi plus 1. Again, this is intuitively clear that the image of this should land in the kernel if you want that the composition is zero. But to prove it, again, I recommend using the universal property everywhere. So once you have this map, then we would like to say when is the sequence an exact sequence. And normally you would say, well, the image should be equal to the kernel as a kind of set in the target. And so instead here, again, we say that the image should be isomorphic to the kernel, like this. So this map here, which we constructed, should be an isomorphism. This means being in an exact sequence of such OX modules. So this was a bit homological algebra. Then we can also repair this definition of the tensor pre-sheaf that we had. Again, we just take this and sheafify it and call the result the tensor sheaf. And then the final bit of definition in this video is when you have an R module M, then you can always take the dual module MV. And this is defined as the module of homomorphisms from M into R itself as R modules. And so you can try basically the same idea to first get a pre-sheaf. And here you have to be a bit careful. So this pre-sheaf takes an open set U, and then you want some homomorphism from F to the structure sheaf like this. The problem is here what we need to take is that you take the homomorphism of OU modules, so a homomorphism of sheaves from this restricted sheaf F to U to the structure sheaf of U. Okay, so let me first finish by saying that you can check this is a pre-sheaf. Again, somehow everything is compatible with restrictions in various ways, and this means that this is a compatible collection of such O of U modules. Again, it will turn out that this is not a sheaf, but only pre-sheaf. So you take the sheafification, and then you get this this dual sheaf, which is denoted by FV, like this. Here you could say, why do we have to do this so? Why do we have to do this so in such a difficult way? Couldn't we just take the more straightforward thing of just saying send you the open set to the homomorphisms from this module to, again here I think it should be OX of U. So just take these two things and take the homomorphisms as OXU modules. So this looks nice, but in fact, this fails a very important property because this is not a pre-sheaf in general. So you should think about why this is the case. Somehow, if you had an open set V inside U, the problem is having such a homomorphism doesn't necessarily tell you how you go from F of V to OX of V, because somehow there's no natural way to go from this F of V, for example, to the F of U. So so you should think it through for yourself, but somehow this here will not give a pre-sheaf in a nice way. You have to take this more fancy thing of saying homomorphisms of OU modules like this. So I know this was a lot of definitions using this new concept of sheafification, but at least for completeness, we wanted to state all of them, and we're going to apply them in different cases in what remains of the lecture. Also have some exercises to make them a bit more familiar. But so here, this is the full list of properties, and now we start using some of them to actually prove stuff.